Hi, I'm Jez Siddons from Peak Electronic Design, and I'd like to show you our latest product, the Atlas DCA Pro, Model DCA75. This has a number of enhancements over our other products, and I'd like to show you some of those features in this video. Some of the obvious main improvements that we have in the DCA Pro compared to the original Atlas DCA is the inclusion of a USB socket and also the use of a graphic display for showing more detailed analysis information and diagrams. I'd like to start showing you some of its capabilities by testing some components that we have here. It can test a wider variety of parts than the standard DCA75. And I'm going to attach the test leads and I'm going to connect it any way around. It doesn't matter which order we connect them. And press the test button. In a few seconds it's going to identify this part for us. And here it's found an NPN silicon bipolar junction transistor. And it's also shown a little symbol there of this particular device. It's identified the pinout, so the red test clip is attached to the base lead. The green is attached to the emitter and the blue is on the collector. Here it's measured the current gain, HFE, of 100. That's measured at a test current through the collector of 5 milliamps. It's also measured the base emitter voltage drop. This has a base emitter voltage of 0.642 volts and that's measured at a base current of 5 milliamps. It's also measuring the collector leakage, and because this is a silicon transistor we don't expect any measurable leakage, and this is showing a current of 0.000 milliamps, certainly less than 1 microamp. And then back to the original result screen. Here's a TO92 style package, so again we can attach the test leads any way around. And this particular part is labelled MPSA 14, so some of you may recognise that already. But we'll see what the DCA Pro says. And here it is showing that it's an NPN Darlington transistor, and the red lead is connected to the emitter, the green is on the collector, and the blue lead is on the base. It shows us a symbol there of this Darlington transistor. And if there are any other features within that package, such as a diode between the emitter and collector, or resistors across the base and emitter, then they'll be shown on that diagram too. And as expected for a Darlington, here we've got a very high gain, 20,600. That's measured at a test current through the collector of 5 milliamps. And typical of a Darlington is also the larger base emitter voltage drop. Here we've got a voltage of 1.434 volts at a base current of 5 milliamps. And hopefully a low leakage current too. Yes, as you'd expect for a silicon device, here we've got a leakage of 0.000 milliamps. I'd like to test another TO92 style package now. And like the other parts, we can attach the 3 leads in any order. And we'll see what the DCA Pro says about this component. So here is an N-channel JFET, and it's identified the pinout. The gate is on the green lead, and the source and drain are both symmetrical, so this particular JFET has interchangeable source and drain leads. That's confirmed on the datasheet for many JFETs. It's measured the pinch-off voltage of this JFET. Here we have a pinch-off of minus 1.30 volts, and that pinch-off is determined when the drain current has reached a value of 1 microamp. It also shows us the gate voltage at which saturation occurs. Here a VGS of 0.19 volts gives you a saturation current of 2.57 milliamps. The DCA Pro also measures the transconductance of the JFET. Here we have 2.9 milliamps per volt over a range of drain current from 1.5 to 2.6 milliamps. The instrument will select a range of currents for measuring the transconductance, and for most JFETs that test current will go up to about 5 milliamps. But for JFETs that have a low saturation current of less than 5 milliamps, then it will select a lower current for the transconductance measurement. And finally, it's measured a drain current of 2.0 milliamps that takes place for a 0 VGS. Now here is a particularly interesting FET. It was highlighted to us by a customer who was interested in testing FETs on the DCA75. This particular FET is actually made from a different semiconductor material called silicon carbide, and if we test this we can have a look at its very unique characteristics. So the DCA Pro has identified this as a normally off JFET. So that means that with a 0 gate voltage there is in fact no current flowing between the drain and the source. And we have the pinout, which has been identified for us. The red is on the gate lead, the green is on the drain, and the blue is on the source. And it's telling us that the pinch-off voltage for this JFET is 0.30 volts. So any gate voltage below 0.3 volts would keep the FET off. And the DCA confirms that it's checked that for a drain current of less than 1 microamp. And the on voltage, the gate voltage at which current flows through the drain and the source, is measured here at 0.69 volts. And that's determined for a drain current of around 5 milliamps. And like the other JFET measurements, the DCA Pro will display the transconductance, 59.2 milliamps per volt for this part, and that's measured over a range of drain current from 3 milliamps up to 5 milliamps. Let's measure a different device, another TO3 style package. I'm going to attach the 3 test leads to this part. This is labelled as a BUZ901. So let's see what the DCA Pro says here. And it comes up with N-channel enhancement mode MOSFET. And the symbol for the N-channel enhancement mode MOSFET is shown on the screen as well. The red lead is identified as the source, the green is showing as the drain, and the blue is on the gate. So pressing scroll we can see some more information. The on threshold is 0.238 volts, and that's the voltage across the gate source terminals that gives you a drain current of 5 milliamps. It also measures the MOSFET's transconductance, and this one is 55.8 milliamps per volt over a range of drain currents from 3 milliamps to 5 milliamps. It's also showing us that this MOSFET has a body diode, and like most MOSFETs there's a parasitic diode between the source and the drain terminals. Unlike the DCA75 product, the Atlas DCA Pro is able to analyse a wider range of parts. And this one here is an IGBT, an insulated gate bipolar transistor. So let's have a look at this. So this has been identified as an N-channel enhancement mode IGBT, and the symbol for that is shown here. The red lead is on the gate, the green lead is on the collector, and the blue is on the emitter. The on threshold is 5.351 volts, and it's quite typical of IGBTs to have a relatively high on threshold voltage for the gate. And that's determined for a collector current of around 5 milliamps. And we've got the transconductance measurement now of 23.7 milliamps per volt. And that's measured over a range of collector currents from 3 milliamps up to 5 milliamps. Moving on to this 3-terminal LED. Attach each lead in any order of course, and pressing the test button we'll be able to see the effect of the current flowing through the LED as the test progresses. Here it says that we have a bicolour LED, a 3-lead type. In this case, it's a common cathode variety. So it's got two LEDs in here, both of which are connected at their cathode terminal. And the DCA Pro will tell us about each LED in turn. So, for the first LED, the green clip is on the anode, and the blue clip is on the cathode. It gives the specs at 5 mA, and for this particular LED, a forward voltage of 1.679 volts. Then we move on to the second LED in the package. The red clip is on the anode this time, and of course the blue is on the cathode, as that's common to both LEDs for this device. We have a slightly higher forward voltage drop of 1.983 volts at 5 mA. Another component that the DCA Pro is particularly useful at analysing is the Zener diode. The Zener diode capability for the DCA Pro extends to nearly 12 volts. So here we attach just two of the three leads, and let's analyse this part. Here it shows that we have a Zener diode, of course, with the green clip on the cathode terminal and the blue is on the anode. And the most important spec for a Zener diode is the reverse voltage, the Zener voltage. This one measures at 5.601 volts at a test current of 5 mA. And this Zener is clearly a 5.6 volt type. It also identifies the forward characteristics, the normal diode behaviour of this part. And here we have 0.798 volts at 5 mA. Like Zener diodes, the DCA Pro is also able to measure many types of voltage regulator, and voltage regulators that have a rated output voltage of 8 volts or less can be measured, sometimes higher than 8 volts if it's a low dropout type. So I've attached the three leads to this regulator, and it's identified that it is a regulator, and it also shows the pinout. The red lead is on the out terminal, the green is on the ground, and the blue is on the in terminal. We can have a look at some more specifications here. The output voltage of this regulator is showing as 7.999 volts, and indeed this is a 78L08 regulator. It's also measured the quiescent current through the ground pin, in this case 3.30 milliamps. It's also determined that this regulator has a dropout voltage of 1.39 volts, so the input voltage needs to be 1.39 volts higher than the output for the regulation to take place. Next we have a very common triac. This is a BTA06 600. The DCA Pro, although it can test thyristors and triacs, the test current is limited to around 10 mA, so not all thyristors and triacs can be analysed by the DCA Pro. The Atlas SCR Model SCR100 is better suited for testing thyristors and triacs that may need test currents of up to 100 mA. So we test this part, and we can see that it's showing the symbol for a triac along with the pinout for this device. The red is on MT1, main terminal 1, the green is on main terminal 2, and the blue is on the gate. And that's a fairly common pinout for triacs that are in a TO220 style package. I'd now like to show you some of the capabilities of the DCA Pro when it's connected to a PC. The DCA Pro is supplied with PC software on the Peak USB flash drive, and the DCA Pro needs to be connected to the PC using a micro USB cable, and one is supplied with the instrument. So plugging it in instantly causes the DCA Pro to wake up and connects to the PC. At the moment we don't have a component connected to the DCA Pro, so we'll do that next. The first component that I'll examine on the PC is another Zener diode here. Just like in standalone mode, we can use the leads in any order. We can press the test button on the unit, or we can press the test button on the PC software. So if I press the test button on the unit, it'll identify this in the usual way. This is displaying Zener diode, of course. And we're showing green clip is on the cathode and the blue clip is on the anode. And we have a Zener voltage of 7.587 volts at a current of 2 milliamps. So let's see the PC software. I'm going to change to the PC view now while this component is still connected. And now we have the PC view of the DCA Pro software. This shows the results of the analysis that we've just taken, and is split into three areas. The left hand side shows the text that is displayed on the DCA Pro instrument itself. The centre area shows a colour version of the pinout, and we can see the cathode is highlighted in green because the green clip is currently connected to the cathode, and the anode is coloured blue because the blue clip is currently on the anode, and the red is not connected to anything. And on the right hand side we see a summary of the accuracy and other limits that apply to the Zener diode analysis on the DCA Pro. So we can have a look at some more information here. If we click on Graphs and PN Junction, we can plot a graph of current versus voltage, and we can have a look at either the forward or the reverse bias characteristic. And as it's a Zener diode, the reverse will be quite interesting. So we can just go with the default values that are here and just click Start, and as the data comes in, the graph will automatically be scaled to fit the graph, and we can see the very nice characteristic of this Zener diode with a good knee at 7.5 volts. On the same graph we can also plot the forward characteristic, so we can change the bias to forward, and again just go with the defaults and click Start. We can see here, of course, this is your standard 0.6 or 0.7 volt characteristic that you would expect to see for a forward bias diode. And if we wanted to copy and paste this graph into a Word document, for example, we may want to just change these legends here. So we can right click on any of these graphs and rename. So let's call this one the Zener forward. And for the red graph, let's rename that one to Zener reverse. And now we're ready to copy and paste this graph, so we can do a right click, copy that image, and we can go straight into Word and paste that. And that's ready to be part of a report, for example. Let's have a look on the PC at the results from a more interesting component. So this is a common 2N3055 transistor that we looked at earlier. And as before, we can analyse by clicking the test button on the PC software or pressing the test button on the instrument itself. And when that's been identified, the results are passed immediately to the PC. And we'll take a look at those now. And here we are with the information that's just been transferred to the PC software. We can see here the text that is displayed on the instrument itself. In the centre we have the pinout confirmation, so we can see here that the blue clip is currently connected to the collector, the red clip is on the base, and it's detected the green clip is on the emitter. And on the right hand side we have a confirmation of the accuracies and the limits of measurement for bipolar transistors when being analysed on the DCA Pro. So if we want to have a look at some graphs of this part, one of the most interesting graphs is a very common graph that you see in datasheets of collector current versus collector emitter voltage. And with these automatically selected parameters here, we can dive straight in and press Start. So we can see here as the information grows, the graph is automatically scaled to fit the information that's been plotted, and so we can see this family of curves growing. So the first base current that it's used for this test is 120 microamps, and it's reducing that in 5 steps down to 24 microamps. So typical of this type of transistor, we have fairly flat curves indicating a fairly constant current gain over a range of collector emitter voltages, but there is a slight slope and higher quality transistors tend to have much flatter responses on these curves. So we can have a look at even more detail if we wish by doing a right click and copy data, and we can now paste all of that data straight into Excel. So if we start Excel, and we can just paste that straight in, and here we can see all of the raw numerical information that's made up all of those curves that we've just seen in the DCA Pro software. And we can pick off any of these columns and start doing graphs or further analysis. So for example, we could have a look at this graph that was done for a base current of 96 microamps. We can select all that data and we can graph that. So if we just pick a simple graph type, a scatter graph, and there we are, there's our graph, and we can add some more information to that or perform further analysis. But with all the information there in Excel, then really it's up to you what you do with all of that information.